Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So in the previous class we will solve some problem, and so in this class, so we will start with a experimental evidence of that the charge is quantized. Okay, so we will start with a problem that is actually the based on the some experiment that is called the Millikan Weyl-Dopf experiment. Okay, so this experiment was the first direct evidence that the charge is quantized. Okay, so start with the experiment that is called the Millikan Weyl-Dopf experiment. So we simplify this by considering a Weyl-Dopf, okay, of charge q and radius r. So it's an Weyl-Dopf of, let us say, charge q and the radius of this drop r becomes 1.64 times 10 to the power minus 6 meter, and we do not know the charge q, okay, of this Weyl-Dopf. We will calculate, and the mass density will 8.51 times 10 to the power 2 kg per meter cube. We use SI unit, yeah, and is allowed to fall from a rest and then enter into a region of constant external electric field A. Okay. So constant external field, that means the uniform, okay, action. So this uniform, there is a direction applied to the downward direction, so now here we consider the electric force, okay, due to this electric field as well as the gravitational force, right. So let us first consider the mass. So the mass of the Weyl-Dopf. So total mass of the Weyl-Dopf, since we know the density, mass density, this m rho Weyl mass density times the volume, and we consider the Weyl-Dopf as a spherically symmetric and sphere, okay, of radius r. So this Weyl-Dopf becomes a sphere of radius r, sphere of radius r. Then the volume is 4 pi r cube rho Weyl times 4/3 pi r cube, right, and we know the radius this, and this is the rho Weyl. So now we substitute this value, okay, so we get this 8.51 times 2 times 4 pi over 3, 1.64 times 10 to the power minus 6, okay. So use the SI unit, so the mass unit is kg, right. This one becomes 1.57 times 10 to the power minus 14 kg, okay. So since the both electric field, okay, and So this the oil drop becomes static when the electric field and the gravitational force and the electrical force are balanced, right. So will be in static equilibrium when gravitation exactly balances okay the electrical force that Fg plus Fe is 0. Okay, this is a vector. Okay, so here we consider the oil drop falls from a rest. Okay, so that's why the gravitational force points downwards. So the gravitational force, since the gravitational force points downward, so the electrical force on the oil must be upward. The electrical force on the oil drop, okay, must be upward, and when they equal, they exactly balanced. Okay, and the system will be in static equilibrium. System means the oil drop. Okay? So the oil drop will be in a static equilibrium. That is the point. Okay. So using our force law, so that means that m g vector plus q e vector. So this is the gravitational force, and this is the electrical force becomes 0, right? This one becomes, if we focus on the magnitude, so m g minus q e y, right? So now the electrical field pointing downwards. So now, so here we consider the electrical field. So this electric field is pointing downwards, right? So that means the charge q must be negative. Okay, the charge on the oil drop must be negative. So with the electrical field E vector downward, so we conclude that the charge on the oil drop, charge on the oil drop must be negative, right? That is the conclusion from this experiment. So because we set up an experiment where the electric field downwards, right, and we know that the gravitational force and electric force are opposites. So that concludes that the charge of an oil drop must be negative. So now we calculate the amount of charge, okay, the magnitude of charge. So basically the magnitude of charge q, so magnitude of charge q mj over ey, right, from this equation. So this one becomes, so you know the mass m, right, we calculated just, yeah, this is the mass of an oil drop, this is a capital M, the capital M. So 1.57 times 10 to the 14 times, what is the values of g, 9.8 in SI units, right, and the Ey, the value of the electric field is given, okay. So Ey, okay, 1.92 times 10 to the power 5 Newton per Coulomb. So 1.92 times 10 to the power 5, so Newton per coulombs, and this one becomes coulomb, right? So the unit is coulomb. So this is the Q. So what is the value? So 8.03 times 10 to the power minus 19 coulomb. So now we know that the charge of a body is a multiple of multiple of basic unit of charge, that is the electric charge, okay, charge of an electron. So multiple of basic unit of charge, which is called the electron charge, right? So we divided by this, so then the number of electrons in the oil drop are n, the number of electrons in the oil drop n by E. So E is the charge of an electron. So 8.03 times 10 to the power minus 19, 1.6 times 10 to the power minus 19. This is 5. Okay, since the n is a number, it cannot be decimal point, it is an integer value, so it is 5. Okay. So if you get a closely to 5, so you approximate to 5, because the n is a number, okay, in the integer value, right, it is a number. So this one suggests that the charge is quantized, okay. That means the charge of an oil drop is some multiple of an electron charge, right. That's conclude that the quantization of charges, okay. So this is basically the quantization of charge, right. Okay, so this one is the last class, and thank you for your kind attention. Okay, so hope you learn better. Thank you.